So today we're going to look at one of our biggest concepts, and that's going to be the idea of forming compounds. We're going to spend quite a bit of time on this, and it's a really important concept if you plan on taking grade 11 chemistry. So before we get too much into the types of compounds, let's start by just talking about the difference between an atom, an ion, and a compound. So atoms we really studied in grade 9. Atoms are a single unit of a chemical element. So carbon, nitrogen, chlorine, those are all examples of atoms. When you were drawing your Bohr-Rutherford diagram, those were atoms. In grade 9, we also looked at ions. An ion is a charged atom. So it's something that's gained or lost electrons. So how do we know it has a charge, or how do we know it's an ion? It's got this charge here. So the fact that sodium has a charge of +1, we know it's an ion. The fact that we know oxygen has a charge of 2-, it's an ion. So it's gained or lost electrons to become more stable. Probably the most common way that atoms become more stable, have full valence electrons, is they form compounds. So a compound is two or more chemicals that have been combined. So how do I know I have more than two chemicals? You can take a look. If you see more than two capital letters, then you know you have two elements that are combined. So in this case, we have two hydrogens and one oxygen. In this case, we have carbon and two oxygens, or we have sodium and chlorine together. So even though this has 4 letters, there's only the 2 capitals, which means that there's 2 elements. So this is actually water, carbon dioxide, and this is sodium chloride table salt. What we're going to know by the end of this entire forming compound section, the most important part is for you to be able to write these chemical formulas on your own. So I can tell you the elements, and you're going to be able to predict exactly how many what the chemical formula is going to be, including these numbers, and also naming. So I might give you a chemical formula, and you have to be able to tell me the name. This is really important in order to be able to communicate in chemistry. So this is a concept that you don't have to record in your notes. We're just going to talk for a little bit, and we're going to talk about why compounds might form in the first place. So elements are going to be satisfied when they have a full valence shell. So by forming compounds, that's a way for us to have a full valence shell. There's going to be 2 different types of compounds we're going to look at: ionic and covalent. Ionic compounds, there's lots of exceptions to the rules. So we're actually going to have 3 lessons on ionic compounds, today being the first one. Covalent compounds, unpredictable, there's a few fewer rules around them. So we're only going to have 1 lesson on covalent compounds. So let's start by looking at ionic compounds. Before we get to the naming and drawing, which is really the most important part, let's just familiarize ourselves with ionic compounds. So here's a little cute meme about ionic compounds and how they form. And if you didn't guess, ionic compounds actually form by ions, right? So we're going to be looking at ionic compounds forming through ions. So you can see we've got our positive ions here. We've got our negative ions here. And it says over here, perhaps one of you gentlemen would mind telling me what outside the window you find so attractive. So really what ionic compounds are going to be is ionic compounds are going to be positives and negatives being attracted to one another. So an ionic compound, it's called an ionic compound because it's made up of negative and positive ions. So you have at least one negative and at least one positive ion. So what that means is how you tell if you've got an ionic compound is you must have at least a metal and a non-metal. Remember that metals always tend to form positive ions and non-metals tend to form negative ions. So if you see both a metal and a non-metal, that's how you know you've got an ionic compound. So the most important thing with compounds to start is identifying whether it's ionic or covalent. So always check, look at your letters, use your periodic table. If you've got a metal present, then you have an ionic compound. Ions and ionic compounds are held together by what we call electrostatic forces between oppositely charged bodies. So in other forces, you've got a negative, or in other words, you've got a negative, you've got a positive. Those 2 forces are going to attract almost like magnets. Let's look a little bit closer on this electrostatic attraction. So we're going to look at the bond that forms between sodium and chlorine. So sodium here has 1 valence electron. It's looking to give up that valence electron. Chlorine here has 7, so it's looking to gain 1 valence electron. So what's going to happen is the electron from sodium is going to go to chlorine. That's not in itself what forms the bond. What's going to form the bond is the fact that we now have a positive, we now have a negative. Those are going to act like magnets. They're going to stick to each other. That's what's forming the bond. So the attraction between the positive and the negative, that's our electrostatic attraction. That's forming your ionic bond. One thing to note is if you take a look, the positive ion is always written first in the name. So our name here is going to be sodium chloride. We're going to look at our naming rules in a second. Our metal is always written first. That's always the rule. So your metal is always going to be found first. Your non-metal is going to be found second. A little bit about properties of ionic compounds. Because the bonds are so predictable, they have very unique properties. So anytime that ionic compounds come together, they're going to form what's called crystal lattice structures. So crystal lattice structures almost look like a checkerboard. It's very, very, very unique under a microscope. So this is what salt actually looks like. So if you actually look at salt under the microscope, they actually look like small square cubes because of that crystal lattice structure. Ionic compounds at room temperature also tend to be hard and brittle. So if you've ever tried to crush salt before, again, it's hard and brittle. They have high melting points, so it's really tough to melt salt. You're not going to see it melt at room temperature. That's because ionic bonds are very strong, so it takes a lot of energy to break them. And oftentimes, ionic compounds will dissolve easily in water. Since ionic compounds tend to dissolve easily in water, they form what's called solutions. So if you've ever tried to dissolve table salt, sodium chloride into water, it dissolves quite easily, and that's going to create a salt water solution. So you might have heard that term before, salt water solution. That's just sodium chloride, an ionic compound, dissolved into water. I mentioned before that crystal lattice structure. So if we actually, again, take a look at sodium chloride under a microscope, this is that crystal lattice structure. So it forms those square little rectangle things here, and it's got a very unique shape that's unique to salt. A little bit about solutions and why they form. The reason that these compounds actually dissolve into water is because one side of water is actually positive and the other side is negative. So since ionic compounds have a positive and a negative, and since water has a positive and negative side, they are said to mix very easily. They're said to be soluble and they dissolve very easily. So that's just a little bit of background knowledge of why ionic compounds dissolve so easily. Because they dissolve so easily and they've got ions floating around in the water, they are said to be good conductors of electricity. So salt water itself is actually a very good conductor of electricity. So you can have electricity flow freely through salt water or any ionic solution. You can test for ions in water as well too. This is sometimes useful if you want to tell how much chlorine is present in your water, or if you want to tell if there's fluoride, which is really good for your teeth, present in your water. These ions react very predictably, so there's certain tests that you can run. For example, you can drop silver nitrate into water, and it's going to test for chlorine ions. So because their ions are present in water, you can't necessarily see them. There's lots of ways to test using outside chemicals. That's a little bit of background information on ionic compounds. Now we are going to get to the very important part, so you're going to want to make sure you take really good notes here. We're going to start with how to write ionic formulas. So what I mean by formulas is I mean that chemical formula we were looking at. So for example, if we were talking about sodium chloride's chemical formula would be this. And I can tell it's this just by looking at the periodic table. So I'm going to teach you how to write out a formula, how to know what numbers, what letters to include, just by knowing what ions are present and by looking at the periodic table. So we're just going to remind ourselves a little bit about ionic formulas. So you don't have to include this part in your notes. We're just going to do a brief overcap of what we did in the lesson before this. So we're going to remind ourselves that an ionic formula or an ionic compound is going to have a positive and a negative charged ion. Overall, the compound itself is neutral. So when I actually write out sodium chloride, sodium and chlorine are going to come together. So sodium is positive, chlorine is negative. They're going to cancel each other out. So overall, table salt is said to be neutral. So even though it has ions in it, overall it's actually neutral itself. We call that charge balance. So the fact that those charges are canceling out, that's charge balance. So if we do this properly, overall, every time we are going to have a neutral compound. So that means our total positive charge is equal to our total negative charge. I know this kind of seems redundant, like I'm saying the same thing over and over, but these 3 points are really the basis of how we figure out the ionic formula that we're going to be looking at. I mentioned this before, but just a reminder that the metal is always going to be written first and the non-metal is always going to be written second. Another reminder of compounds, the chemical formula, the symbols of the elements are written with subscripts, which indicate how many of that element are present in the compound. Only numbers above 1 are written. So I'm just going to give you a couple examples of what I mean here. Let's talk about sodium chloride. We've seen that before. I keep bringing it up. It's a good common example. So notice that when I write sodium chloride, there's no numbers present. What that means is I have 1 sodium and 1 chlorine. We don't write 1, we write anything above 1. If I want to write calcium chloride would be written like this. This number 2 here indicates the fact that I have 2 chlorines. So these 2s are written as subscripts, or these 3s or 4s are written as subscripts. And what it means is you have 2 of this element that's right before it. So our chemical formulas that we're going to be writing are going to consist of both letters, and they're also going to consist of numbers telling us how many atoms we have. So again, we're not going to include this in our notes. We're just going to talk here, and we're going to show you how to figure out how many ions you want to have or what numbers you need, and we're going to use this idea of charge balance. So let's talk about sodium chloride. We've seen how it works before with the electrostatic electrostatic attraction. We've gone over it a couple times, so we're going to show you again how to figure out how many sodiums and how many chlorines there are in sodium chloride. So let's take a look at our sodium atom first. Our sodium atom is going to lose its valence electron to chlorine. Chlorine is going to gain that electron. So overall, we have 1 sodium and we have 1 chlorine. What's important is this charge here. So sodium here, I have a plus. Chlorine here, I have a minus. For ionic compounds, again, we always want to have charge balance. So to check to make sure that my number is correct, we're going to take these 2 charges and we're going to add them together. If they equal 0, we're good. If they do not equal 0, you need to add in more negatives or more positives to get it to equal 0. So if I take positive 1 and I add to it negative 1, that's going to give me an overall charge of 0. I've got charge balance. What that means is I've got 1 sodium and 1 chlorine. So I would write this as sodium chloride, NaCl. Again, the metal written first and the non-metal written second, right? So that's not too bad. We've looked at that before. Let's look at another example of magnesium chloride. So again, you don't need to include this in your notes. This is the long explanation of charge balance and how this works. I'm going to teach you a shortcut after this that you're going to use. Shortcuts are useless though, unless you understand the principles behind it. So these principles of charge balance are going to be important. So let's take a look at magnesium chloride and let's figure out how the heck did we know that there's going to be 2 chlorines and only 1 magnesium. So let's take a look. Let's look at a magnesium atom here. A magnesium atom is actually going to want to lose 2 valence electrons. Chlorine is only going to want to gain 1. So magnesium has to lose 2. That means there must be 2 chlorines present. 1 chlorine to take the first electron, the second chlorine to take the second electron. So in order to have balance, we have to have 2 chlorines to make this work. It's almost like a puzzle, right? If we only had 1 chlorine, we would have an extra electron and it wouldn't have anywhere to go. So magnesium, since it's lost 2 negatives, magnesium has an overall charge of 2+. Since we have 2 chlorines, we have 1 negative and we have a second negative. So if I were to take 2+, and I were going to go ahead and take away -1 for my first chlorine and take away -1 for my second chlorine, I would get a total of 0 charge balance. So that charge balance is again what tells us how many of each atom I want to have in my ionic compound. So I know I have 1 magnesium, Mg. I know I have 2 chlorines, so I'm going to put a little 2 next to chlorine. So overall my chemical formula is going to be MgCl2. My metal is always written first. My nonmetal is always written second. So that's the principles behind charge balance. Now that we understand the principles, I'm going to teach you a shortcut, and it's going to be much easier for you to predict how many atoms are going to be present in each compound. Before I get to that though, I want you to pause the video, and I want you to go ahead and figure out the charge balance for Na2S. How did I know that I actually had 2 sodiums for only 1 sulfur? All right, so let's talk about this charge balance to make sure that you really understand. So if we're looking at sodium and sulfur, sulfur is going to have 6 valence electrons. Sodium has 1 valence electron. So sulfur is looking to gain 2 electrons. Since sulfur is looking to gain 2 electrons and sodium only has 1, I must have 2 sodiums in order to donate those 2 electrons. So I must have 2 sodiums in order to donate those 2 electrons. That means I have 2 positives and I have 1 charge of 2 negative. So again, if I go through and I go positive, positive, minus 2, I'm going to get what's called charge balance. So my formula is going to be Na2 for 2 sodiums, my metal written first, and sulfur. We call that sodium sulfide. So that's how charge balance works. Let's scroll and let's look at how to actually write ionic formulas from charges. So charge balance is used to write the formula for sodium nitride, a compound containing Na plus and 3. So we're going to look at how to actually figure out charge balance without having to draw the compound. So we were drawing out my ions before. We don't need to do that. We're going to look at how to actually figure that out. So I have sodium and I have nitride. Nitride has a charge of 3 negative. In order to cancel out this charge of 3 negative, I must need 3 positives. Since sodium only has a charge of +1, I have to have 3 sodiums in order to cancel out this 3 negative. So overall, 3 positives, 3 negatives is going to give me charge balance. So my formula for sodium nitride would be Na3N. So you can see how already this is shorter to figure out than to actually draw each one of the Bohr-Rutherford diagrams. Now that we understand charge balance, I'm going to give you a set of rules that you're always going to follow when you're writing ionic formulas. So your first rule is always going to be double check you have a metal and a non-metal. If you don't have a metal, you're actually not dealing with an ionic compound, and these rules are not going to work. So always double check to make sure you have a metal and a non-metal first. Next, you want to identify the charge of each ion. So just a reminder that you can use the periodic table to identify the charges of each ion. Remember that anything in group 1 is +1. This is +2. Over here is +3. Then we have -1, -2, -3. So you can actually use the periodic table, and you want to go ahead and you want to list your charges. We're then going to use what's called the crossover rule. And that's going to ensure that each compound is balanced. Now, I'm going to cover the crossover rule in a little bit more detail later, but let's use our example from above to show you the crossover rule. So remember that we had sodium and we had nitrogen in our example before. So my chemical symbol for sodium is Na, and my chemical symbol for nitrogen is N. Next up, I want to identify the charge. So sodium has a charge of +1. Nitrogen has a charge of -3. So what the crossover rule is going to do is it's going to actually take my charges and it's going to cross them. So it's going to bring my charge of sodium and it's going to write it next to nitrogen. And it's going to bring my charge of nitrogen and it's going to write it next to sodium. It's going to cross over. So let's see what that's going to look like. I'm going to write Na. And then whatever charge nitrogen had, I'm going to write it next to sodium. But instead of writing it up here, superscript, which means charge, I'm going to write it down here, which means the number of ions. So for the charge for nitrogen, I see a 3, so I'm just going to write a 3. You don't need to include the negative or the positive, because remember that negative and positive are going to cancel out. Now I'm going to write nitrogen. And then I'm going to take a look at the charge up here. Now there's nothing written, so remember, if there's nothing written, that means there's a 1. Well, rule number 4 says that I do not need to write 1. I don't have to put a 1 here. The fact that there's no number means that there's actually 1. So we actually just leave this as it is. This is something that's got charge balance. So I know the chemical formula for sodium nitride is Na3N. One last rule, if the charges are the same, you don't need to record the subscript. So if these were the same number, if this was a 3 and this was also a 3, I actually don't have to write either 3. I'm going to show you an example of that in a second. So now that we have an idea of this, we are going to do some examples. So I'm going to go ahead, I'm going to use this whiteboard as some examples, and I'm just going to give you a couple elements and we're going to practice these together. So I'm going to start with kind of an easy one. I'm going to start with sodium. And I'm going to start with fluorine. So here I've got sodium, here I've got fluorine. So what I want to do is I want to use a periodic table to check their charges. So sodium is in group 1 and fluorine is going to be in group 2. What I'm going to do while I'm here, group 17. What I'm going to do while I'm here though is to make sure that I actually have a metal and a non-metal. So sodium I can see is in the metal category. Fluorine over here is in the non-metal category. So I do have a metal and a non-metal. I do have an ionic compound. So let's go ahead and record my charges for sodium, +1. We're going to record my charge for fluorine, -1. And now I'm going to go ahead and I'm going to do that crossover rule. So I'm going to bring the charge for sodium down here. I'm going to bring the charge for fluorine down here. And I'm going to write this out in good. So in good, sodium. Now I'm going to go ahead and check my charge for fluorine. Well, that was 1, and I don't have to write a 1. Fluorine. Going to check next to sodium. Well, I see a 1. That means I also don't have to write a 1. So my chemical formula for sodium fluoride is just NaF, and that means 1 sodium and 1 fluorine. Not too bad. So let's look at one that's a little bit more complicated. Let's look at lithium. And let's look at sulfur. So again, I'm going to make sure I have a metal and a non-metal, and I'm also going to check the charges on the periodic table. So let's start with my non-metals this time. I see sulfur. Sulfur's in group 16, so that means it's got a charge of -2. I'm going to switch to my metals. That didn't work. There we go. I'm going to switch to my metals. I see lithium is over here. So lithium's in the first group. That means it has a charge of 1. So lithium has a charge of +1. Now I'm going to go ahead and I'm going to do that crossover rule. So the crossover rule, I'm going to bring the charge of lithium down here. I'm going to bring the charge of sulfur down here. And I am going to find I've got a lithium. Now sulfur has a 2 written next to it, so I want to put a 2. I'm then going to write S for sulfur. Lithium has a 1 written next to it. Remember, I don't have to write a 1. So overall, I have lithium sulfide with 2 lithiums and 1 sulfur. All right, I am going to give you another example now. We are going to look at calcium. And we are going to look at nitrogen. I want you to go ahead. I want you to pause the video, and I want you to see if you can figure this one out on your own. So I'm going to go ahead over here, and I'm going to check on my periodic table. I'm going to look at calcium, which is a metal, and calcium is a metal. It's got a charge of 2+ because it's in the second column. So where'd I go? There we go. I'm going to go ahead, and I'm going to record my charge of calcium here as 2+. I'm then going to go back to my periodic table. I'm going to find nitrogen. Nitrogen is a nonmetal, and it's over here. Nitrogen has a charge of -3, right? -1, -2, -3. So it's found right here. So I'm going to go ahead and record my charge of nitrogen as 3-. Next up, I've got that crossing over rule. So I'm going to go ahead, I'm going to bring the charge of calcium down here. I'm going to bring my charge of nitrogen down here. And I'm going to find that I'm going to write my chemical formula. I've got calcium. And nitrogen has a charge of 3-, so I'm going to write a 3 here. I've got nitrogen. Calcium has a charge of 2+, so I'm going to write a 2 here. If you actually want to take a second and figure out charge balance, figure out what the charge of calcium is, figure out what the charge of nitrogen is, what those are going to add to, you are going to find that this has a charge of 0 when you actually add them up. One more challenge that I want to give you. Note that I said challenge. Beryllium oxide. So why don't you go ahead, pause the video, and you try to figure these out on your own. So we're going to start with oxygen because that's what's up. Oxygen is my nonmetal, and oxygen has a charge of -2 in this column. So I'm going to record the oxygen over here as -2. Beryllium is a metal. And beryllium over here has a charge of +2. So I'm going to record the charge of beryllium over here as 2+. Last thing I'm going to do is my crossing over rule. And once I do my crossing over rule, I'm going to see that I'm going to write beryllium here. And I'm going to write oxygen here. Beryllium has a charge of 2. Oxygen has a charge of 2. So that's it, I'm done, right? Just a reminder of that last rule, and that last rule, I'm going to scroll for a second. If the charges are the same, you do not need to record the subscript. So when you get here and you see these charges are the same, you actually don't need any subscripts. They're going to go ahead, they're going to cancel each other out. So what that means is we're going to have beryllium oxide. Also the same, you can reduce subscript as well too. So you're not going to see it in grade 10. You might see it in grade 11. If this was a 2 and this was a 4, you could go ahead and reduce those by using common denominators. So it'd be BeO2. So anytime you have the same number, then you want to go ahead and you want to cancel them out. All right, now that we've dealt with the formula part of ionic compounds, we are now going to look at naming ionic compounds. Naming ionic compounds is much easier than the formula. So once you've done the formula part of it, which you just did with that crossover rule, naming is much easier. So we're just going to go ahead and we're going to take a look at these steps for naming. First thing you want to do, same as the first rule for formulas, always double check you've got a metal and a nonmetal. These rules only work for ionic compounds, so you always have to make sure you've got that metal and that nonmetal. The name of the metal is always going to be written first. The name of the nonmetal is always going to be written second, but what's going to happen is you're always going to use the ending "ide." So if you've been paying attention while I've been naming these compounds as we go, I've always been using the end "ide." Sodium chloride, hydrogen sulfide. So that "ide" ending is just what we do when we're naming compounds. So what you want to do is you want to drop the first part of the drop the second part of the nonmetal and add an "ide" ending. So for example, oxygen becomes oxide. Chlorine becomes chloride. Can take it just a little bit of practice, but the more you hear ionic compound names, the more you're going to figure out when to drop the ending and when to include the "ide." So we're just going to do a couple examples right now. I'm going to give you some chemical formulas and you would go ahead and you would name them. So let's take a look at the first one. Let's look at this one here. So we've got CaF2. So first thing I want to do is I want to make sure that I actually have a metal and a nonmetal. So we're going to take a look here. We've got our metal is calcium. And we've got our non-metal over here is fluorine. So in order to name this, all I need to do is write the name of the metal first. That's calcium. I leave a space. I write the name of the non-metal second. That's fluorine. But instead of writing fluorine, I'm going to write fluoride. This 2 here, right now for naming, means nothing. So the 2 means that I have 2 fluorines. In terms of the name, you don't need to indicate that in the name. Let's look at another example. Let's look at this. Li2. Oh. So let's look at our periodic table. Li stands for lithium, and it is a metal. Oxygen, O stands for oxygen, which is a nonmetal. So in this case, to name this, I would just call it lithium. And then I'd leave a space, my metals first, and rather than writing oxygen, I would call this oxide. Last one that we're going to look at, I'm going to give you another one. Let's go Ki. So we're going to go to our periodic table again. We're going to find I down here is iodine. That is a nonmetal. K is potassium. It is a metal. So in order to name this, I would call this potassium. Picked a long one. I would leave a space, and then my second part of my word, iodide. And that is it for naming. So I did say it's going to be easier than the formulas. So the formulas are the tough part for regular ionic compounds. The naming is the easier part. So that's the end of this lesson. This is kind of part 1 of 4 of naming. Tomorrow we are going to look at what's called multivalent metals in ionic compounds. Have a great day. We'll see you soon.